Okay, thank you for joining us this morning on our webinar for getting started with the OCS. Video is roughly 27 minutes thereabouts, and afterwards we'll go back to the webinar page and we'll go through what's coming up and where you can view the old ones. And yeah, if you have any questions throughout, please put them into the questions panel and we'll get through them at the end. Okay, let's get going.
Hi, today we're going to be getting started with Horner's all-in-one controllers. We're going to cover the following topics. We'll start with model selection, followed by software setup, making a connection, configuring hardware, programming logic, and finally building screens. With this start, you'll be knowledgeable and productive when you use your OCS on your first project. Let's take a look at model selection. This isn't an exhaustive comparison between all the different OCS all-in-one controllers, but a quick reference for you. We've got 4 primary product groups that you can see here. Let's start with the Micro series. There are currently 4 models in the line, ranging from the 2-inch key-based model X2 up to the 4-inch and 7-inch touchscreen versions X4 and X7 and the 10-inch X10. The Micro series is best for simple applications. It's got a slim design, can support up to 5,000 logic variables, and has 2 built-in I/O options ranging from 26 to 30 I/O. It doesn't support CAN Open, J1939, or MQTT IoT protocol. Now let's talk about the XLE and the XLT. These products offer great control with a basic user interface. They can be DIN rail mounted, so if you're looking for a PLC without a significant user interface, these products are right for you. They support double the amount of logic variables that you'll find in a Micro series, and they have more flexibility in the built-in I/O, with up to 5 I/O options ranging from 22 to 42 total I/O points. They support several of the protocols that the Micro series does not, including J1939 and CAN Open, but the XLE and XLT do not support MQTT. Now for the Mainstream XL series. This is our most popular product line, with touchscreens varying from 4-inch to 15-inch. They support 50,000 logic variables, and they offer 5 I/O options just like the XLE and XLT, with some of these options having higher analog resolution. For the XL7, XL10, and XL Plus, you get dual Ethernet and dual CAN, and the 15-inch XL Plus expands the video features to full screen. Finally, let's take a look at some of our specialty controllers, the X5 and the RCC. They're great products but aren't our most popular. The X5 offers a unique combination of features with its form factor similar to the Micro series, and its processing power similar to the XL series. The RCC is basically an OCS but without a screen. The RCC 6512 has both co-processing and high-speed counting. Now onto the software setup. To start programming your OCS all-in-one controller, you need to download Cscape. It's free, but there are some requirements. First, you'll need to register on our website. Next, you'll need to log into the website, navigate to the Cscape download page, and answer some simple questions. Pick out the specific Cscape version you'd like, and then download the install package. Here is my Cscape install file after I've unzipped it and moved it to my desktop. You have to be an administrator to load the install file. We'll fast forward through the setup as it's quite user-friendly and self-explanatory. Next, let's make a connection between Cscape on our computer and our new OCS all-in-one controller. The controller I'm going to get started with today is the Micro X4. I've got one powered up here through 24 volts. It's face down on the table, and I've yet to connect it to my computer. Before I do that, I want to make sure that Cscape is looking for the right target ID for the controller. Every OCS shipped from the factory has a target ID of 253. That happens to match the CScan ID. In the lower right hand corner, it shows we have no communications, because I haven't connected my computer to the OCS yet. It also shows target 1. We don't want target 1, we want target 253. To change that, we press the target icon and set the target for Cscape to look for a 253. It's asking if we want to open hardware configuration. No. Now it's looking for the right target. I'm going to plug in my USB cable. The first time you plug it in, Windows will busily load the communications driver so it can talk to the OCS. In my case, the driver was already loaded. I still don't have communications, so let's look at Windows and see if we can find the OCS connected to one of the COM ports. I'm going to select the device manager and look for ports COM and LPT. There we go. USB serial device COM8. That's the COM port that the OCS is connected to. I'm going to close the device manager and go back to Cscape. I'll go to the controller menu and connection wizard. Here I'll select USB. Sometimes it doesn't find the port on the list here. In that instance, we'll select serial. Then we'll manually fill in COM8 as the port number. Once you're done, hit finish, and in the lower right hand corner of your screen you can see local 253, target 253. Now let's configure that OCS. Okay, we're back in Cscape. To configure the hardware, we need to go to the hardware configuration section from this icon here, or from the controller menu. By default, it is still using another controller, because the OCS was not connected when I started Cscape. If I had the X4 connected and it was talking when I started Cscape, it would have automatically selected my micro X4. To connect it, there are some different options. I can manually find the micro OCS here, so I select micro OCS series and then I select the model, which is an X4. It gave me a warning that the total number of programmable screens in this unit is 250, which is less than the XLE that was previously configured. I'll just hit OK. Then I have a choice between the X4R and the X4A. I will select the X4R. Instead of all that, you can hit the auto configuration button. Again, it gave me that same warning, and it's automatically selected the correct controller. So that's how you select a controller. Next, we need to configure the built-in I/O. To do that, let's go to the local I/O tab. Here you'll see a side view of the controller, and you can hit a config button that shows you the I/O map. There are 4 different types of built-in RealWorld I/O in an OCS controller. You have I for digital input, Q for digital output, AI for analog input, and AQ for analog output. These are the default number of each of those memory types that are configured to the controller. To set up the individual I/O, let's go to Module Setup. You'll see 4 different categories: digital in and high-speed counting, digital out and PWM, analog in, and analog out. Let's start with digital in and high-speed counting. In applications where you aren't high-speed counting, the only thing to configure is whether you want positive or negative logic on your inputs. Positive logic is where you run a positive signal, for example 24 volts, into the digital input. Then when it sees a high signal, it will turn on. Negative logic is when the input is looking for 0 volts in order to turn on. If you have high-speed counting in your application, there are up to 4 high-speed counters to allocate. By default, they are disabled. Let's start out by looking at the options for input number 1. I can count frequency, I can totalize or count positive transactions, I can measure the width of a pulse, or I can connect a quadrature type signal. For demonstration, I'm going to be counting pulses on high-speed counter input number 1, so I'll select totalize. I'm going to be counting the rising edge. If you just want to count inputs without a maximum, then you can leave that at 0. The only time you'll set that to a non-zero value is if you are using an encoder. And in the application, it's a rotary application, where there are a maximum number of counts per revolution, and you have exactly 1 revolution for your mechanical system. If you have more than 1 revolution, leave that at 0. Other options include pulse width, where you're measuring the width of a pulse, and quadrature, where you're connecting an incremental encoder. For an encoder, you're going to select the style. Do you want the first encoder input to lead the second, or do you want the reverse? We'll select 1 leads 2 countdown as it's most typical. For more information on encoder applications, you can see our pre-recorded video for encoders. Okay, so that was a look at high-speed counter, but I'm going to select disable. In my application, there is no high-speed count. Next, let's look at the digital outputs. For most applications where you're not doing any high speed on your outputs, you're going to leave the 2 high speed outputs at normal. That's really all there is to it. The other option you have with the X4R model for each high speed solid state output is you can configure whether those are wired as syncing or wired as sourcing. This applies to all of the R models in the micro series. If you wire the output as sinking, you can drive half an amp on the output side. If you wire it as sourcing, you can drive around 50 milliamps. If you're only using the output to drive a high-speed output, sinking is almost always the better choice, unless the amount of the load that you're driving is very small. The last thing to configure is what happens to your outputs when the controller goes into stop mode. Most of the time that will be default, so that when the controller goes into stop mode, all of the outputs turn off. In the rare occasion where you want different behavior, you can make an output turn on power down, or to hold the last state on power down. Now let's look at the analog inputs. By default, all 4 analog inputs are disabled. You want to configure those for a different range if you're actually using them. In the case of the Micro X4, you choose between 0 to 20 milliamps, where 0 counts as 0 milliamps and 32,000 counts as 20 milliamps, and 4 to 20 milliamps, where 0 counts as 4 milliamps and 32,000 counts as 20 milliamps. If you have a value below 4 milliamps coming in, you will get a negative reading that will tell you that you've got an issue on the sensor. So for the best resolution, 4 to 20 milliamps is the better choice. Finally, you can select RTD PT 100 on each channel. With a micro series, you are limited to a temperature range of -50 Celsius to +200 Celsius. For most applications, that's perfectly fine. You've also got a filter constant, which you can set to a value between 0 and 7. This allows you to select between fast response and steady readings. 0 means there's no filtering, so every scan, the controller takes the analog to digital conversion and reports it directly to the analog input register. If you set it to a value of 7, the maximum value, you're going to have the smoothest signal, but with the slowest response. Finally, there's a configuration register. For advanced applications, if you want to change the sensor type on the fly, then you could select a variable or register here, but I'll leave that alone. Finally, let's configure the analog out. There's little to configure on the analog output side, besides whether you want the channel disabled or you want 4 to 20 milliamp mode. Once that's configured, you can decide when the controller stops whether it holds its last value or goes to a value of 0. Most of the time, you want the value to go to digital 0, which is equivalent to 4 milliamps when the controller goes into stop mode. You could also assign a variable here if you like. So that was the I/O configuration. Now let's discuss programming logic in Cscape. Now before we dive into programming logic, the OCS memory structure is an important concept to understand. There are 4 different types of RealWorld IO memory. Those are I for digital inputs, Q for digital outputs, AI for analog inputs, and AQ for analog outputs. There are also internal memory types, %T or temporary for non-retentive bits, %M or maintained for retentive bits, and then some general purpose word type registers %R, which are retentive 16-bit words. There are also special memory types with predefined values. There are S system bits and SR system registers, which again are 16-bit words. So that's the OCS memory structure. There are 3 different options for programming logic in Cscape. Advanced ladder, which is register based, advanced ladder, which is variable based, and IEC 61131. I'm going to use the most basic, advanced ladder, which is register based. We have plenty of resources online to show you the other programming styles. Okay, we want to do a simple ladder logic program. You have your programming environment here, your project toolbox is here, which has all the different instructions you can use for advanced ladder, and then you have your project navigator over here, which is a way for you to get around your program and navigate through the configuration. We're not going to spend much time on the project navigator today. In the center section here, I have some common elements that are used with ladder logic programming, including a normally open contact. I'm going to click on one here and drop it in column A. It doesn't matter where in column A that I click, it'll start the rung here. Now a screwhead has appeared, which shows that a rung has started. I can now continue to draw my logic by dropping another, or I can change to a different element and drop that, or I can go back to my pointer device. And I can double click on the element I just dropped and configure it, or assign it a memory address. Let's do that here. With register-based advanced ladder, for every variable you create, you need to assign its memory address. This contact I just dropped is part of the start-stop circuit. Let's say it's a hardwired start push button. and it's wired to the 5th digital input point. Let's type in %i5 in address and then name it whatever we want. I'll call it start_push button. So I've created a start push button contact. Let's say that when I press the start push button, I want to turn on a motor starter, which is a coil. I'm going to select the coil and then drop that somewhere on the right. With Cscape, you can have programs up to 30 columns wide. My coil needs to be the rightmost element on the line. I'm going to select my pointer, double click the coil, and assign it. Let's say it's connected to the first digital output, which is Q1. In this case, I didn't type the %sign. Most of the time, you don't have to type the %sign. Cscape knows what you mean. And I'm going to name this motor starter. So I've created some basic logic, which says when I press the start push button, the motor starter is going to turn on. This isn't going to work very well, because as soon as I let go of the start push button, my motor starter will turn off. Let's seal around the start push button, so that when I release it, the motor starter will keep going. That means I need a parallel contact. I have the vertical branch tool here, so I select that and I'm going to place the branch underneath and to the left of the start push button, and then somewhere to the right I'm going to put another branch. I'll select a normally open contact, drop that contact, go back to my pointer and double click it. Now for a seal contact, we want to use the motor starter, which is Q1. I can pull it off this drop down list if I don't remember what I had named it, and then I'll hit OK. Now when we press start push button, the motor starter will start and we'll seal around it, so when we release the start push button, the motor starter will keep going. I have no way of stopping my motor starter at the moment, so let's grab a normally closed contact as our stop button, and let's assign it its address. Let's say it's the 3rd digital input wired to the start push button. I'm just going to type in i3 or %i3 or even 3i. Cscape works with all of these. I'll name it stop push button and hit OK. We've now configured our first rung of ladder logic. Let's say that we want to time how long the motor starter is running, and then after 10 seconds we'll turn the motor off again. So I want to start off with a contact in column A to start a new rung. Now if I don't drop the contact in column A, let's say I put it here, a new rung won't automatically start. I can put it here, but I have to manually start my rung. I can do that by switching to the pointer, right-clicking here in this area, and pressing New Run. Now I've got the screw head, which is our indication of a new rung. I've got the contact I've just dropped here, and I'm going to assign it. Let's make this the motor starter, because that's what we want to detect and start timing. There are a couple of different places we can find timers. They're in the toolbox, under Timer Counter Operations, but they're also listed here in the Center Convenience area. So I'll select a timer, and I'm going to drop it and go back to my pointer. Now with some PLCs, you have special memory address types for timers. The OCS isn't one of them. The OCS uses general purpose word type registers for timers, and it uses 2 of them consecutively. I'll type in %r1, I'm selecting a general purpose register with my R type, and I'm picking number 1. This is what will be assigned to the timer. R1 is the first 16 bits and is my accumulator, which is timing or accumulating time value. The second 16-bit register, which is R2 in this case, is going to be a housekeeping register. Every timer that's a 16-bit standard timer takes 2 consecutive word type registers. I will name it starter timer. This can be on either an on delay timer or an off delay timer. It can delay turning on or delay turning off. We will make it on delay. Resolution ranges from 1 millisecond up to 1 second. Let's say we want to time the motor starter running to 10 seconds. I'll set my preset value to 10 seconds and in 100 millisecond counts. That is a preset value of 100. When my accumulator reaches a value of 100, my timer will time out and pass power flow from the left to the right at that point. If I want my timer to remember its value through a power cycle, then I'll make it retentive. If I wanted it to clear itself automatically each time it loses power coming in, then I can leave it as non-retentive. I'm going to leave it as non-retentive. I've got a timer. This is going to time to 10 seconds. When that's up, I want to turn on an internal contact. It's internal because it's not directly wired to a real-world output, so I'm going to pick an internal type bit. I could pick from many different types. M's are maintained bit types, T's are temporary bit types, and both are internal. I'm going to use a T type here. I'll start at T1 and I'll name it motor starter 10 seconds. So what's showing here is we've assigned a non-retentive timer. Whenever the motor starter is not running, the timer will reset to 0. Whenever the motor starter is running, it will count to 10 seconds. Once it reaches 10 seconds, it will turn on this output, bypassing power flow. Now let's make this T1 contact into an automatic stop button. I'm going to go up here, select normally closed contact, and put it in series because it's a stop contact. I'll double click on it and call up the T1 bit I just configured. Now after 10 seconds of running and the timer expiring, the motor starter will automatically stop. Next we're going to show you how to configure screens. To start programming user interface screens, we go to the Cscape screen editor by pressing this View/Edit Screens button here. What I'm looking at here is an OCS screen. Every OCS can be configured for a certain number of screens. I'm working with a Micro X4, which is good for up to 250 screens, and other controllers can do even more. I'm on screen number 1, which has little asterisks showing that it's the default or initial screen. So far, we've programmed a simple start-stop circuit with real-world start and stop push buttons. So let's throw an indicator on the screen as a quick start. These are all the different graphic type objects that I can put on the screen, and this is a text object. If I wanted to put a title here, I could click on this text object, drag it, and let go. Click again so you can see the size of the object you've created. I'll double click on it and name it Operator Station. On this first screen, I'll center the text, and I'll make the color red and the font a bit larger. I'll hit OK. I can drag these out to make it obvious that my text is centered. I've got a simple title, and we've got a variety of different objects here. I'm going to start with an indicator. That indicator is the equivalent of a pilot light that we use to turn on when our motor starter is running. So I clicked on the indicator and dragged it to size. Now I'll double click. First step is to assign an address to cause this indicator lamp to light up. I'll assign motor starter, which was Q1. If you don't know the address, you can select one from the drop-down list. Now, by default, when this turns on, it's green, and when it's off, it's red. I'm going to change the on color to bright red and the off color to dark red, and then I'm going to hit OK. You'll see it says lamp. That's not what we want. We want it to say motor starter. I'm going to double click and go back into the object, and under legend, I'm going to make this motor starter. I'm going to leave the font relatively small and hit OK. Now we have a basic two-dimensional pilot light. We'll assign a 3D bezel to it. You can also change the shape of the light, but we'll leave it round. Hit OK. Now we have an indicator that turns bright red whenever the motor starter is running. When the motor starter is not running, it will stay dark red. I have a little test button here, or operator simulator, that I can select, and then when I click, it'll show me what the changing indicator will look like. Let's make the operator have the ability to start the motor from a push button on the touchscreen. I'm going to select a switch object, drag it onto my screen, and resize it. I'll double click on it. This is a parallel push button. It'll cause my motor starter to start. This is not going to be wired to a RealWorld IO point, so I won't assign a person or %Q type register or memory address here. I will use one of the internal bits because this is an on-off. I can use either a T or an M, where the only difference between them is that the M's are maintained to a power cycle. That doesn't make sense for a push button on a touchscreen, so I'll select a T. I assigned T1 earlier in my program, so I'll assign this T2, and I'll name it Start TS for touchscreen. When the button gets pressed, T2 is going to turn on. Down here under Legend, let's call this Start, and let's leave the font size small. When we configure the switch, we'll change the shape to something similar to the indicator. Let's make it round with a 3D bezel. And then under Indicator Properties, when it's on, we'll make it bright green. When it's off, let's make it dark green. That's just when we're pressing it. And we'll hit OK. Now we've configured a basic start push button. I'll go ahead and make it the right size. I now have a start button and an indicator. Let's say I want a stop button that can also be operated from the screen. Instead of creating a new one from scratch, I'm going to copy and paste this one and move it over here. I'll double click on it. We need to give it a new internal bit because it's a different operator. Let's make it T3 and name it a stop TS. Under Legend, let's say stop, and let's change the colors on the indicator. Again, let's make the center color bright red when it's on and dark red when it's off. Okay, So we've got a start button, which we've assigned to T2. If I don't remember which one was assigned to it, it shows me when I hover over the object. If I hover here, it should show T3. If I hover here is Q1. This is Q1 because the bit that turns on the real-world wired motor starter is the same bit that causes this light to turn on. That's why that has a RealWorld IO point. So we've just done this simple start, stop, and motor starter indicator. Let me close this here and go back into our logic. Let's add in our parallel start and our series stop. I'm going to click on my branch tool and click here and here before and after the start. Then I'll add my contact using the drop down. Hit OK. Now I need another series stop button. I'll put it here, anywhere in line would work. This one was T3. I now have modified my logic to include operators from the screen, not just from the real world. Now I've done my program, let's download it into the controller. To do that, I need to make sure that I'm talking to the controller, which I am in the lower right hand corner. You see local 253, target 253. Then I hit the download button. It asks me to use smart load, which says it's going to download any items which have changed. I'm going to hit OK, and then the download process is starting. When the download is complete, let's look at what's going on. This is a good time to learn about debug mode. This is the mode in which we can monitor our program and debug it. You enter debug mode through this debug button here at the top. I've pressed it. You have to be connected and online with your controller. The operators that are able to pass power flow are shown in red. Nobody's pressed the start button yet. All of our stop buttons are allowing power to pass through them when the power arrives, and the motor starter is not running, the timer is not timing. This is what we expected to happen. Let's flip over the OCS here and look at the screen. That's the screen we've created. Now if I press the start button, we should see things happening. There we go. Our middle operator has started. The motor is running, our timer is timing, and when it gets to 10 seconds, boom, our T1 bit will go off, which has caused an automatic stop of the motor starter because that T1 bit was in series with the start-stop circuit. Hopefully that demo helped you get started with OCS in your all-in-one controller. Thanks for attending today's tutorial. The Q&A session will begin shortly.
Okay, we'll just see what questions are in there now. Do we have a document on the system register bits? These can be found in the help file of Cscape. So you can just type in %SR into the search bar of the help file and you'll have the full list of what they are and what they cover. I often get errors when trying to do auto config. That is most likely because you're trying to do it before adjusting your target to match your local. That's always the case when that happens. Is there anything else coming in? Does not appear to be anything else. I'll take you to the webinar page there now and I'll show you what's coming up. Just 2 seconds there now. Okay, so you should all hopefully see my screen there now. Okay, so next week we do have the Horner IO review, same time as usual next Thursday, and then the following week we have the high-speed counter review. So both registration links are there right now. So if you wish to register, you can do that now. As always, you can view previous webinars down below. We'll upload them all as soon as we can. Can you make your own library in Cscape? Is this, do you mean a library of programs, or you can have your Cscape files all saved in a folder on your PC, which you can always just open into Cscape. There'll be no fear of that. I'm not entirely sure what you mean, your own library. If you want to drop text port an email after, we can clear it up. Yeah, perfect. Yeah, I think that's it for today. Thank you all for joining us. And Again, if would love to see you next week for our upcoming webinars. So hopefully we will, and we'll talk to you then. Goodbye.